Greetings of the day. Myself, I am Dr. R. Venkat. I'm working as an associate professor in the Department of Computer Science and Engineering. Today, I'm going to discuss about a topic called Knapsack Problem, that is using backtracking. That is from the course called Analysis and Design of Algorithms, which is simply called as EDA. Even this course is also called as Design and Analysis of Algorithms, that is DA. And in some universities they call this one as Algorithm Analysis, that is AA. This is an extension for Data Structures course. So in some universities with data structures means DS plus AA, simply they refer this course as Data Structures and Algorithm Analysis. So from this course, I'm going to discuss a topic called Knapsack Problem. So regarding Knapsack Problem, first I will try to discuss about what do you mean by Knapsack Problem. So it's Knapsack Problem. So what is knapsack problem? So this is a knapsack. So the K is silent. So this is the way how we need to pronounce. That is knapsack. Knapsack. Okay. So this K is silent. So regarding knapsack problem, what is this knapsack means? Knapsack is nothing but it's simply a bag. It's simply a bag, or even it can be a container. But try to remember one thing, that in examination you should never use a word called bag or container. Yeah, it's a bag or a container, but the thing is that we should not use these words. We should refer that one as knapsack only. This is just for an understanding purpose. I am saying that it's a bag or a container. So then what is knapsack problem? So we will have a bag and we will be given with some objects, just like let the objects be object 1, object 2, object 3. Like that we will be given with some n number of objects. So for every object there will be a weight Wi, and also every object will have some profit Pi. Okay, such that what is knapsack problem means, so this bag will have some capacity. Let the capacity be some m. So we will be given with some objects and we need to fill this knapsack with these objects, such that the total weight of all these objects should not exceed this m, and we need to get maximum profit. Means, so you can fill the bag with any number of objects, so that should not exceed the capacity of the bag, means that is m. So for example, if I actually fill the bag with 3 items, that is object 1, object 2 and object 3, means let the weight of the first object be W1 and the second object be W2 and the third object be W3. So this should not exceed the maximum capacity of the bag. So this should not exceed the maximum capacity of the bag, or it should be equal to the maximum capacity of the bag, that is m. And we need to get the maximum profit, such that so we can have many solutions here, but the thing is that we need to go with the optimal solution. What is optimal solution here means whatever gives the maximum profit. So, so now I think regarding knapsack problem, we can solve this problem using many ways. We have many problem solving strategies for solving knapsack problem. So, so, so what are the different ways in YADA? What are the different ways to solve this problem? Uh, so what are the problem solving strategies we are having in order to solve knapsack problem in analysis and design of algorithms? We have many ways. We can solve the problem using backtracking. We can solve the problem using greedy method. We can solve this problem using dynamic programming. We can solve this problem using branch and bound, that is FIFO branch and bound, and also using least cost branch and bound. So we have some 5 problem solving strategies to solve knapsack problem. So in those, let me discuss how to solve knapsack problem using backtracking. So once again, just I am discussing, we can solve knapsack problem using some 5 problem solving strategies within analysis and design of algorithms. The first way is backtracking, the second way is greedy, the third way is dynamic programming, the fourth way is within branch and bound. We can go with FIFO branch and bound, and even we can go with LC branch and bound. So within all these 5 problem solving strategies we are going with, I am going to discuss how to solve a knapsack problem using backtracking. Before going to the problem, let me discuss this one with a example. So for example, we have a let me take a situation where we have a farmhouse and we have a bullock cart. So this farmhouse actually it is attacked with some fire. So within some 10 to 15 minutes, this whole that whole farmhouse will be burned. So within this 10 to 15 minutes, we need to we have few items within the farmhouse. So we need to fill our bullock cart with some items. Means we can't save all the objects within the farmhouse, but we need to plan such a way that we need to fill this bullock cart with few objects, such a way that we need to get the maximum profit. For example, so within the farmhouse you can have many objects. You can have some platinum, gold, silver items. You can have some groceries. You can have some home appliances or electronic appliances. So first priority we need to give for platinum, gold or silver. We need to give first priority for platinum, gold and silver items, and the second priority we need to give for any kind of home or electronic appliances. And third priority we can go for some groceries or for some fruits or some vegetables or something like that. We need to fill the bullock cart. Bullock cart is just like some knapsack. It's a container. We need to fill this particular knapsack with some objects such a way that we need to get the maximum profit. If we can fill the bag, we need to give the first priority for platinum, gold, silver or any kind of diamond items, because they are very expensive. If we can save them means we can get maximum profit. Then we need to give the next priority for any kind of home or electronic appliances, because uh, what to say, after gold, silver and platinum items, the most expensive items are some home and electronic appliances. So like that, we need to plan, or we need to plan what to say, we need to fill the knapsack with some objects where we can get maximum profit, because that bullock cart, which is the container, which is just like knapsack within this particular situation, it is just like some knapsack. We need to fill that one with some objects such a way that, what to say, we need to fill that one with some items such that it should not exceed the capacity of that particular container or bullock cart, because that bullock cart will have some capacity. We can't fill that bullock cart with all the items within the farmhouse, but we can fill that one with some items such a way that we need to get the maximum profit. Before the complete farmhouse is burned, we can save few items which are expensive. Like that, we need to plan what to say, such that the way, what to say, the way how we actually fill our bag or the knapsack, okay, with those items we need to get the maximum profit. So we can fill the bag with any number of items, but optimal solution is nothing but whatever gives us the maximum profit. So now let me go with the problem. So here we are going to solve this problem using backtracking. What is this backtracking? Just I will give a brief idea regarding what is backtracking. So backtracking means, actually here we actually go with a starting node. So means actually here in backtracking we start from a starting point. From there, with the available proofs or with the available references, we need to go with some set of possibilities. So if you think this way is the first possibility, means we need to go until the dead end. If you think this is the dead end means, so we need to stop here. Why? Because from here what to say, we don't have any way to go. So then again we need to come to the starting point. Again we need to come to the starting point, and again with another possibility we need to go with the other possibility we need to go until we find the proper solution. If you think this is dead end, so again we need to come back. Again we need to go with the next possibility. So what we are doing here, so here, so every time with the available possibilities we are going up to the dead end, and from there, here we don't have any option to go forward. So what we are doing means we are again coming back to the starting node, that is, or to the starting point, and again we are going with the next possibility. If you have any possibility to get the solution means, we will go from what to say, we will try to go with the set of sub possibilities. If you don't have any possibility and if you think that is the dead end means, again we will come back. So every time, for every possibility, we are going up to the dead end and we are actually coming back, means we are, what we are doing here, we are coming back and again tracking the next possibility. That's the reason we call this problem solving strategy as backtracking. Here we start with we actually start from a start node with the what to say, with the available constraints or with the available what to say, possibilities. We go with each possibility up to the dead end. So if you think that is dead end, and if you think what to say, if we think there is no possibility, or if you think there is no path to find the solution, means we stop at that particular point and we actually come back and we track Again we track from the starting node. So every time we actually go with a possibility until the dead end, again we come back and track from the starting node with the next possibility. That's the reason we call this technique as backtracking. So in order to solve knapsack problem using backtracking, we need to go with a state space tree technique. So before going to discuss about state space tree, in order before solving the knapsack problem using uh, state space tree, let me give a brief idea regarding what is the difference between knapsack problem and 0 by 1 knapsack problem. We have two ways here. One is a knapsack problem, another way is 0 by 1 knapsack problem. One way is knapsack problem and another way is 0 by 1 knapsack problem. What is this knapsack problem? What is the difference between knapsack problem and 0 by 1 knapsack problem? Knapsack problem means here both are same, but the thing is that we have a small difference between knapsack problem and 0 by 1 knapsack problem. In knapsack problem, what to say, for example, if I can take a home means, what is within our home we will have some electronic appliances just like some television, some air conditioning. Okay, so when you want to fill your knapsack with these kind of items means, if you take a TV, if you take a television, how you can what to say, how you can fill that particular television within the knapsack means you need to take the whole TV. You need to consider the whole TV. Here our object is a TV or a television. So if you want to fill this particular knapsack with this particular object means we need to consider this whole object, because you can't break the television and you can't take some fraction of that particular object. You need to consider that whole object. Okay, so it means that you are considering that whole object, then it comes under 1 into object. Even if you take air conditioning or if you take refrigerator also, you can't take fraction of those items. You need to consider those whole items. If you think considering those items actually that exceeds the maximum capacity of this bag means you need to ignore that item. If you ignore such items means then you need to mathematically we show that one with 0 into object, means we are ignoring that object. If we are considering that object means mathematically we show that particular what to say, considering that item as 1 into object, means we are considering that object. So if you can take some groceries, so other than these objects, if you take any grocery type of items means within groceries you can have many things. You can have some what to say, some oil, okay, some what to say, some pulses, okay, you can have some what to say, cookery items, okay, you can have some multi-purpose powders, okay, just like that we can have many things within groceries. So when we can take these groceries means you can take some fraction of these groceries. For example, if you are going to any picnic means no need to take all the grocery items within your home. You just what to say, plan your picnic or your outdoor what to say, your outdoor if you go, if you actually how you will plan your items for the picnic means you will try to take some few groceries whatever required to cook some food outside. So you will plan like that. So within the groceries you can have fraction of some items. So for example, if you think the groceries, the entire groceries as 1 means, okay, you can take what to say, 1/4 of groceries for outing. You can consider 1/4 of the groceries. So if you take any kind of fruits or vegetables means, okay, you can take within fruits you can plan some few apples, few oranges, like that. You can have fraction of these items. For example, what is the knapsack problem means, within knapsack problem you can consider the whole item, that is 1 into object, or you can ignore that item 0 into object. If you ignore means that comes under 0 into object, or even you can consider some fraction of some items. The fraction can be with anything. Fraction of 1 by, that can be 1 by 10 or 1 by 4th or 1 by 2. Okay. So within knapsack problem, you can fill the knapsack with the whole item, or you can ignore that particular item, or you can consider fraction of that item. So that comes under, if we go with these three constraints means, that comes under knapsack problem. Then what is 0 by 1 knapsack problem means, here 0 means we are ignoring the object, and 1 means we are considering the item. It means that in 0 by 1 knapsack problem, the only possibility to fill the bag is, you need to fill the bag with the whole object. Then that comes under 1 into object, means we are considering the object. Or if you think that object actually exceeds the maximum capacity of the bag means, we need to ignore that item. So we can't consider fraction of that object within 0 by 1 knapsack problem. So this is the difference between knapsack and 0 by 1 knapsack problem. In knapsack problem, we can consider the whole item, or we can ignore that item, or even we can consider fraction of that particular item. Whereas in 0 by 1 knapsack problem, we have only two ways. That is, one is if we consider that item means 1 into object. If you ignore that object means 0 into object. 0 by 1 means, 0 means we are ignoring the object. 1 means we are considering that whole item. Whereas knapsack problem means we can consider the object, or we can ignore the object, or even we can go with fraction of that object. This is the general difference between knapsack problem and 0 by 1 knapsack problem. So now let me take a problem and let me solve this one using backtracking. So here, in order to go with backtracking problem solving strategy means, we need to construct a state space tree. So let me take the problem. We are given with some 4 items, that is n is equal to 4, and and the maximum capacity of the bag m is equal to 8, and the weights of the objects w1, okay, w2, w3, comma w4 is equal to 2, 3, 4, 5, and the respective profits of each item is p1, p2, p3, p4 is equal to 3, 5, 6, 10. So if you consider first object means, the weight of that object is 2 and the profit we get is 3, and the maximum capacity of the bag is 8. Okay, so now let me construct the state space tree for the given input. as this state space tree will be very big. That's the reason just I need some maximum space to construct this one. So no, just I'm in a simple manner I'm writing the input here. So just I'm writing the weights and profits of each object on the top. So here we represent each node with the weight of the object and the respective profit of that particular object. So here we are actually we are going to construct the state space tree here. So now let me take the root node. So within this root node, first I am actually I'm considering the first item. So the first item weight is 2. So I'm considering the first item and the weight of that particular object is 2, and the profit whatever we get for that particular object is 3. So now we have two possibilities. The first one is first possibility is we need to consider the first object. So another possibility is we are not considering the first object. So now let me write here. So that is x1. We actually represent the possibilities with xi. x1 means first object. x2 means second object. So I value is nothing but that represents the object. So x1 is equal to 1 and x1 is equal to 0. x1 is equal to 1 means we are considering the first object within the knapsack. x1 is equal to 0 means we are ignoring the first object. So if we consider first object, within the root node already we considered the first object. Within the root node we already considered the first object, so we will get the same node, that is first object weight with the respective profit of the first object. So if we don't consider first item means nothing but we are don't consider any object means we are not considering, our knapsack is empty, means the weight filled within the bag is 0 and the profit we get is 0. So from here we need to go with the next possibility. First let me expand this one. Let me expand this particular node and we will go. First let me go with the possibilities when we consider the first item. Okay. So the next possibility is nothing but x2 is equal to 1 and x2 is equal to 0. What do you mean by x2? x2 means we are representing here xi means regarding the object. If I value is equal to 2 means it means that it's regarding the second object. If x2 is equal to 1 means we are considering the second item. If we consider the second item, okay, what we need to do? Nothing but if we are considering the second item means what is the weight of the second item? The weight of the second item is 2. Okay, it means that, so now we considered first item and second item. So now just add the second object weight to this first object weight, then the total weight is 5. Similarly, just this is the profit of the first item. So if we consider second item, the weight is 2 plus 3, we get 5. Similarly, if we consider second item, we need to add this profit of the second item, that is 5 to this 3. Then we will get 8. So the thing is that Now if we don't consider second item, okay, here we are not considering the second item. So if we don't consider second item, we will get the same output. So that is, already we considered the first item, so we will get the same output. So now the next possibility, that is x3 is equal to 1 and x3 is equal to 0. What do you mean by x3 is equal to 1? Nothing but we are considering the third item. Now we are considering the third item. Okay, if we consider the third item, just what to say, so just I am writing the profits also here, 3, 5. If I consider the third item, what is the weight of the third item? The weight of the third item is 4 and the profit we get is 6. So now we need to add this 4 to 5. Then we will get 9. And the profit we get is nothing but, the profit whatever we can get is 8 plus 6. 8 plus 6 we will get 14. But here there is a problem. Here the maximum capacity of the bag is 8. But here if we put all these 3 items, means the weight nothing but we will get 9, means the total weight of the objects whatever we put in the knapsack are 9. So this exceeds the maximum capacity of the bag. In that case, so this solution is not a feasible solution. So we need to, what to say, we need to kill this particular node. Why? Because this is an infeasible node. Yeah, though we get a profit of 14 also, so the total weight of the object should not exceed the maximum capacity of the bag. So now let me go with the next possibility, that is x3 is equal to 0. If we go with x3 is equal to 0, then we will get, it means that we are not considering the third item. In that case, we will get the same output, that is 5, 8. So now let me go with the next possibility, that is nothing but x4 is equal to 1, x4 is equal to 0. So if we consider fourth item, so without considering, so now we are considering, just see what is this one. Okay, we are considering first item, second item, and we are not considering the third item, and we are considering the fourth item. So we already considered the first two items, we are not considering the third item. x3 is equal to 0 means we are ignoring that particular item. So nothing but what happens here. So if, and we need to consider the fourth item. So just what to say, what is the weight of the fourth item? The fourth item weight is 5. Okay, the fourth item weight is 4. Okay, sorry, 5. And the profit we get is 10. So now just add this 5 to this 5. Then we will get 10, comma, and we will get a profit of 10 plus 15, 18. So here, just see here. So here the total weight of these objects actually exceed the maximum capacity of the bag. Just like this node is also not a feasible solution. It's an infeasible solution. So kill this particular node. So now now we are ignoring the fourth item. So here we already ignored the third item. So we will get the same output, that is nothing but we will get the same output, 5, 8. Yeah, here we are considering the first item, second item, we are not considering the third item and fourth item. So we will get the same output. So now let me go with, let me expand this particular node. So here, so again x3 is equal to 1 and x3 is equal to 0. If we consider if we consider the third item, so just add the third item weight for this particular 2. So what is the weight of third item? 2 plus 4, that is 6. And the profit of third item is 6. 6 plus 3, 9. So now if we don't consider the third item, we will get the same output, 2 comma 3. So now let me expand this particular node, that is 6 comma 9. That is x4 is equal to 1, x4 is equal to 0. So if I consider the fourth item, okay, this is x4 is equal to 1 means we are considering the fourth item. So if we consider the fourth item, then just see here. So the weight of the fourth item is 5. 6 plus 5, 11. So no need to go with the profit. So already 11 means it exceeds the maximum capacity of the bag. So it's not a feasible solution. So till this particular node. Okay. So now let me go with the next possibility. If we don't consider the fourth item means we are considering the first item, we are not considering the second item, we are considering the third item, and we are ignoring the fourth item. It means we will get the same output, that is 6 comma 9. Okay, and let me expand this particular node, that is, okay, x4 is equal to 1, x4 is equal to 0. If we consider the fourth item, here we are considering the first item, we are not considering second and third items, and we are considering the fourth item. So the fourth item weight is 5. Okay, 2 plus 5, that is 7, and add this profit for this particular 3, then we will get the profit 10. So is it a feasible solution? Yes, it's a feasible solution. Why? Because the weight of the total items, okay, the weight of the total objects within the knapsack don't exceed the maximum capacity of the bag. Yeah, 7 is less than 8. It's a feasible solution. Even this is a feasible solution. Okay, this is also a feasible solution. Okay. Okay, if we don't consider fourth item, we are considering only the first item. In that case, we will get the same output, 2 comma 3. So in these, okay, the feasible solutions are 5 comma 8. Okay, that is we are considering only first item and second item. So we need to check from here, from the root level. We are considering first item, second item, and we are ignoring third item and fourth item. That is, so nothing but I am just writing like this. We are considering first item, that is 1, second item 1. We are ignoring third and fourth item. Then we will get a profit of 5 comma 8. Okay, and what to say the next one? What to say 6 comma 9. So here regarding this particular node, okay, we are considering first item, we are ignoring second item, third item, and considering the fourth item. So that is nothing but, sorry, we are considering the first item, we are ignoring the third item, we are considering the third item, sorry, we are ignoring the second item, and we are considering the third item, and we are ignoring the fourth item. So this is nothing but 1 0 1 0. So what is this ones and zeros means? In the first place, this represents x1, x2, x3, x4. If x1 is 1 means we are considering the first item. If x3 is equal to 0 means we are ignoring that particular item. So what is the meaning of this one? Means we are considering only first and third items, and we are ignoring second and fourth items. Then we will get a profit of, then we will get, this will be one solution. Okay, what is the next one? 7 comma 10. So just we are coming from here. So we are considering the first item, we are ignoring the second item, we are ignoring the third item, and we are considering the first we are considering the fourth item. So nothing but this one is nothing but 1001. Okay, so here this is the possibility. A minute. Yeah, just this is 13. The first item profit is 3 and the fourth item profit is 10. So just by mistake I actually written 10. Okay, so 2 comma 3 is not a proper solution, so just ignore that particular node. So this is these are the possible solutions. These three are the possible solutions whatever we get when we consider the first item. So as the state space tree is very huge, so now let me go with the next possibility. So for that one I am just erasing this one. I'm going with the next possibilities. If we don't consider first item, how many feasible solutions we will get, and we need to go with the optimal solution. So what is the optimal solution? Whatever gives the maximum profit among all these solutions. So we got some 3 solutions here. So among all these solutions we need to consider a solution whatever gives the maximum profit. So now let me go with, if we don't consider first item, so the next possibility is we can expand this node as x2 is equal to 1, x2 is equal to 0. So if we consider the second item, nothing but simply add the weight of the second item, that is 3 comma, the profit is 5. Yeah, and if we don't consider the second item, then we get 0 comma 0, we get the same node. So the next possibility is nothing but x3 equal to 1, x3 is equal to 0. So if we consider third item, just add the third item weight for this particular second item weight, then we will get 7 comma 11. Okay, and if we don't consider the third item, then we will get the same output, that is 3 comma 5. Now if we consider the fourth item, means x4 is equal to 1, x4 is equal to 0. So if we consider the fourth item, means, so 7 plus 5, how much we will get? We will get 12, and the profit is nothing but what to say, the profit of fourth item is 10, so we'll get 21. Yeah, so the total weight of all these objects is 12. So this exceeds the maximum capacity of the bag, so simply kill this particular node. Why? Because this is not a feasible solution. So if we don't consider fourth item, we will get the same output, that is 7 comma 11. Okay, this is one possibility. Okay, just let me write that one. So here we are ignoring the first item, that is 0, 1, 1 and 0. So this gives an output of 7 comma 11. Okay, so now let me expand this particular node. x4 is equal to 1, x4 is equal to 0. If we consider the fourth item, means just add the fourth item weight to this particular weight, that gives 8 comma, so add the profit 15. So the maximum capacity of the bag is 8, so the weight of all the objects is 8. So this is we can accept this solution. Why? Because that should not exceed the maximum capacity of the bag. The total weight of the objects within the knapsack should not exceed the maximum capacity of the bag, but they can be equal to the maximum capacity of the bag. 8 is equal to 8. This is it's a feasible solution. So now if we ignore the fourth item, means we will get the same output, that is 3 comma 5. So now the next possibility is we can expand this particular node as x3 is equal to 1 and x3 is equal to 0. If we consider the if we consider the third item, means, okay, what is the weight of the third item? That is nothing but third item weight is 4, 4 comma 6. Yeah. And if we ignore the third item, means again we will get the same output, that is 0 comma 0. Now let me expand this particular node, that one as x4 is equal to 1 and x4 is equal to 0. If we consider the fourth item, then we will get, okay, what is the weight of the fourth item? 5. 4 plus 5, 9. 6 plus 10, that is 16. Yeah. So this exceeds the maximum capacity of the bag. So kill this particular node. Why? Because this is not a feasible solution. If we don't consider the fourth item, means we will get 4 comma 6, the same output. So now let me go with the last node. Okay. So if we, okay, that is we are considering the fourth item and we are ignoring the fourth item. If we consider the fourth item, then we will get an output of 5 comma 10. Yeah, if we don't consider, then we will get 0 comma 0. So how many possible solutions are there? Is one more solution, that is nothing but this is one more feasible solution, just will come from the top. We are considering the first item, we are ignoring the first item, that is x1 is equal to 0. We are considering the second item and we are ignoring the third item, and we are considering the fourth item. So this is nothing but 0 1 0 1, means we are considering second and fourth items. This gives an output of 8 comma 15. So these are the possible solutions. Among all these solutions, okay, this particular solution, that is ignoring the first item, considering the second item, ignoring the third item, and considering the fourth item, gives us the maximum profit, that is 15. And it don't exceed the maximum capacity of the bag. So among all these solutions, among all these feasible solutions, this is the optimal solution for the given problem. So let me write the output. As we don't have enough space, just I am rubbing this particular state space tree. So the optimal solution, okay, among all the feasible solutions is nothing but 0 comma 0 comma 1. Okay, let me write more detail. That is 0 1 0 1. Okay, that gives the node value is 8 comma 5. That is we are considering second item and fourth item, and we are ignoring first item and second item, x1, x2, x3, x4. So we get a maximum profit of 15. This is the optimal solution for the given problem among all the feasible solutions. So this is regarding 0 by 1 knapsack problem using backtracking. Thank you.